Okay, so I would just like to remind all y'all that the homework 12 is extraordinarily optional, the most optional thing ever. This is called Are You Attending Class and or watching the video and or actually reading the assignment in front of you? Because homework 12 will take off points if you turn it in. You are welcome to do the sucker. It's got some exercises, some challenge problems that you may find useful. But as I've said now twice, as I have put on the assignment itself, it's not yet posted. It will be by tomorrow. As I put on the assignment and as is going on the recording right now, you should not, in fact, submit the sucker. Are there any questions about whether or not this optional challenge assignment is not a bad idea to think about, but do not actually hit submit? Yeah. I'm making this, by the way, to make it further harder to not think about and just do it. I'm making this one and only PDF assignment. I'm putting together a PDF with challenge problems, and it's not going to be on mastering like usual. I think I've previously said a couple of times that what's on mastering is authoritative. If it's on mastering, you should do it, unless specifically instructed otherwise. Well, here's something that's not going on mastering. So hopefully, unless people are really determined not to pay attention, not to listen, you will avoid losing points by doing 12. Okay, and again, I also leave this up to you to decide whether to tell the people who are not paying any attention to let them reap the consequences of their behavior, or to just tell them so that they don't lose the points. That is your decision. I cannot police that. I would like to go back now to something back, not to the future in this case, but back to, it's not an example, it's a scenario, a setting that, as you've seen it on two tests before, may hint, suggest that it'll be on the final. And that is in multiple places, and that is elevators, elevators. It's a great opportunity to talk about a couple different forces, and in this case, to talk about energies. All right, so let us consider the following. We're going to do this for the entirety of today in different ways. I have an elevator in an elevator shaft, and there is going to be a spring at the bottom of the elevator shaft. You guys have seen that, right? And bigger things, those are springs at the bottom. From what I've heard, I'm not an engineer, but from what I've heard, those are actually to make people feel better about the elevator. People with anxiety, make them feel better about it. The actual thing that catches the elevator is not the spring at the bottom. There are really, really fail-safe brakes in the railings. At least that's what I've been told. Let's not deal with the brakes friction just yet. I'll add that in a minute. Instead, there's going to be an elevator with combined mass, you guessed it, M, supported by a cable. We're going to deal with frictionless stuff at first. And the elevator is going to go up from floor, what? Floor 2 to floor 4. I want to end up here. And here's some people. Oh, well, maybe that's my son. Small people. Here. Oh, by the way, during group activity time, let me encourage you to actually pay some attention and put your trust in and hear the advice with just as much care as you would with me, I hope, to Dr. Cerny Joshua in the red shirt up in front. She happens to be not just a, in my view, world-class mathematics. Okay, well, at least national class. Can I say that? Can I say that you have done things on the national level? For mathematics education and research in how students learn or do not learn mathematics well, she also has degrees in both physics and mathematics all the way up to the PhD level on the mathematics side. And you should really listen to her advice. Her advice about how to engage with the mathematics of a problem is better than mine, as she literally has her doctorate in it. So she's at some point maybe going to walk around and poke you guys, look over your shoulders. Please do engage with her because she is a really good opportunity at this point. Yes, Dr. Nalo Tucker is still in training in the blue shirt. Yes. Oh, by the way, he's gone at this point. This is evidence, by the way, that if I give you a problem involving my son and myself, that my son is in fact of smaller mass than I am, that you can safely make the assumption that my 9-year-old son is indeed smaller. Okay, let's do this sucker. Elevator, we're going to start out with a person on an elevator. Good God, that's a long neck. Person gets onto an elevator, the elevator goes up. The combined mass, here's a person on an elevator. Let's not have the people, these people are walking away. They just got off the elevator. I'm not going to treat the people getting onto the elevator as its own thing. Let's just talk about the process of the elevator going from floor 2 to floor 4, okay? No friction. No friction in the rails. I mean, hell, the rails don't even appear to be touching. Let's start by talking about what forces, Google Form A, and Google Form B, what form or forms of energy you would use to analyze this problem. Ready, set, go. Again, Google question A, what forces do you think we should apply in analyzing this situation as we go from floor 2 to floor 4 with no friction? And what form or forms of energy? I will give you 10 seconds. Okay, 1 minute. Oh, and as I've been saying, I would like you to identify forces. You don't need to use triplet notation here, but I don't want you to write out the word. I don't want you to write a paragraph. I don't want you to write a sentence. Please just write the symbol. T for tension, F for friction, W for weight, blah, 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 blah. Okay? For the energies as well, please do not write out words. If you want to talk about gravitational potential energy, use the 2-letter symbol that we've been using, UG, so on and so forth. Oh my goodness, people are paying attention. Breaks my heart with happiness. What's S? Oh, spring force. I was writing FS, wasn't I? Whatever, I understand what you mean. Okay, one more time, let me describe the scenario. We're going to ignore friction. We're going to talk about that later. There is a spring down here. There is a cable attached to the elevator, pulling it upward. We're going to talk about the process of the elevator moving from the 2nd floor to the 4th floor. Question A, what forces apply in this scenario? How would you model this? Question 2, what energy forms apply? Thirty seconds. What did I give one more? Oh, yeah. Um, uh, 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 wait, FS? Elastic. I used F elastic? What did I freaking use this freaking semester for freaking spring force? Did I use FE or did I use FS? FS is static friction, as I was notating that. Did I double a notation? Oh my goodness, I am embarrassed. Okay, well, let me take the suggestion of somebody who said spring force is capital S. Oh, I'm so embarrassed. Let's talk about these forms. I'm not saying that this is the correct answer, by the way. What did we start with? Kinetic energy. We talked about gravitational potential, spring potential, which I call UE, external works. Yeah, let's talk about each of these. How do we identify if a normal force is acting on something? When do you see normal forces? What kinds of scenarios? Please. Two solids touching each other. Or is the elevator touching another solid surface? Well, I mean, there's the rope, but how do we deal with ropes? Tension. So normal does not apply here. Does weight apply? Every elevator I've ever seen is on Earth. Yeah? Does tension apply? Yes. How do you know? There's a rope. Does static and kinetic friction apply? How do you know they don't? Because the professor specifically said we're going to start not talking about friction. Does spring force apply? Sorry for the stupid notation, by the way. I'm sorry. Does spring force apply? There's a spring in the problem, isn't there? Is it touching the elevator? Not at this time. If ain't no touchy, no acty. If it no touchy and no weighty, no acty. So the correct answer for this part, neither normal, static, kinetic, nor spring force. The correct answers are W and T to analyze for this phase of motion. What forms of energy do we have? How do we do that checklist? K, what is required for you to have K? You have to have motion. Is the elevator moving? Now, as we will discuss, we will calculate in a little bit the motion energy for a practical sized elevator. That motion energy is really quite small compared to its potential energy change. We'll see that in a minute. So in a practical calculation, you'll see that you could actually sometimes drop that out. We will start by calculating it. You don't know how fast the elevator is going. Maybe it's Willy Wonka's great glass elevator shooting up there. We'll discuss that. But for now, I would say, yeah, it's reasonable to be considering elevators in motion, so sure. UG, is UG applicable here? You betcha. And where is UG equal to 0, by the way? How do you know when there is or is not? Please. Please. That's right. Anywhere, as long as you define it one time there per problem, anywhere can be, I have 0 potential energy there. But as long as height is changing, it can't start and end at the same vertical height. Potential energy is changing. You have to consider it. UE, there's a spring. Is the spring compressed or extended as we go up from 2 to 4? No way, Josue. Work. Are there any other forces that do work on the elevator? I mean, there are only 2 forces. There's only 2 forces. Let's consider. Is weight already being considered, perhaps? Hint, hint, yes. Is there any other force acting on this elevator that might apply a tension force? Giving it away right there. Yes, we should absolutely include the force of tension in this problem. There is an external work that's not already accounted for. I would say there are 3 forms of energy, and one of them is going to be small. Did you get that? You remember the force parts that identify whether things touch, whether they interact? Okay, well, let me give you some numbers here, some practical numbers. Can do an analysis. We could do an analysis in a numerical fashion. I'm going to say that the velocity of the elevator, in this particular case, upward velocity, is how fast does a fast elevator go? Let's say 1.5 meters per second. I think that's actually way too fast. We're going to go a displacement upward 2 floors is something like 8 meters. What else am I going to give you? A practical mass of an elevator is, I have no clue. I'm guessing, I suspect about 2,000 kilograms might be reasonable, including passengers. And what else? I'm going to say, incidentally, that this velocity is steady. I'll tell you that the acceleration is zero. Of course, at the moment we're starting, at the moment we're stopping, you have to have some acceleration to move. You have to have some acceleration to stop moving. But for the vast majority of the elevator's motion, there's a little jolt at the beginning, moves steadily, little jolt at the end. Let's not talk about the jolts. Let's just talk about when it's moving steadily at 1.5 meters per second. Okay. Now, from this, I would like you to calculate as many things as you can in this problem. As many of these quantities involved, both forces and energies. And we should break this out, shouldn't we? We should break this out so that I can see where you're struggling and what you're getting. So let's say C is calculate, I'll write it this way, calculate, Google question. C is weight force. And I'm going to decorate the forces with their vector signs and put them in the order that I wrote them before. Now, here is a collision that I can't avoid. These really are the standard symbols used in my preferred notation. Yes, W and W have the same symbol. Remember that a vector sign over the top indicates a vector. Work is not a vector. Weight absolutely is. So is tension. Every force is a vector. Every energy and change in energy is not. Ugh. Okay. Can you do this? Sure you can. And I've overspecified the problem. I've overspecified the problem. We can use this to find velocity. We don't need to assume anything at all. No, we didn't. I didn't, because I didn't tell you the work. Whew. Okay. God damn it. No, excuse me. I did specify the problem. I'm so embarrassed. You do not have delta y in this. I'm going to take away delta y. I'm going to ask you to find it. You can use the earlier parts to find the displacement. And no, you can't. Oh, for goodness sake, I am not on fire today. I do have to give you delta y. I'm giving you delta y back. I'm so sorry. This is embarrassing. Once I introduce an acceleration, it will no longer cancel out delta y. Giving it back. My apologies. As my son said at age 3, Papa made a mistake. Question. Yeah, I'm going to. But if you don't, I'll still accept the answer. Ah. Please pay attention to signs, by the way, S-I-G-N-S. They're important. Hey, one more minute to get as far as you can. And we'll discuss each one and see where to improve, where. Kimmy, so as I was describing before, in a real elevator, yeah, you've got to accelerate from being at rest at one floor to being at rest at to being at rest at the fourth floor. But let's not model that. That's a short jolt at the beginning, a short jolt at the end. The majority of the time that the elevator is moving, it's moving steadily, slowly and steadily upward in this case. So we're not going to talk about that yet. We'll model that next. We'll discuss this accelerating phase next. So to finally answer your question specifically, we are going to assume that the velocity starts and ends at 1.5 meters per second. Okay, and we've got a lot of correct answers. Muy bien. Let's dive into these. Weight force. There is a simple equation. Weight force is, hopefully you remember mg. Let's plug in mg. To be precise, if I wrote the vector sign on top, negative mg, right? If I'm talking about the vector itself, I very often talk about its magnitude and direction separately. And if I write that vector sign on top, I'm specifically talking about the vector. So what is that? 2,000 kilos times 10, oh my God. Negative 20 kilonewtons, negative 20,000 newtons. Tension force, which direction is the tension force? It had better darn well be upward. Hey, what's the equation for tension? Trick question. There is no foundational equation. You have to deduce it based on what's going on. Tension doesn't have one fixed equation. For this problem, what did tension better well be? 20K, 20,000 newtons. How do you know it's got to be the same as weight in this problem? If you're not accelerating, F equals ma says, if A is 0, total force has to be 0. Force and downforce have to be in balance. If we've got negative 20,000, there must also be 20,000 newtons upward. Yes, absolutely, Yummy. If you put 19,600, that's perfectly acceptable. Negative and positive, respectively. Okay, so that's the old force method. Let's talk about our new energy methods. What's the equation for kinetic energy? Hopefully you remember it's half mv squared. And if I plug in the numbers, about 2,250. No, actually that one works out exactly. Okay. I want to reflect on this exactly as I said before, half a second. Exactly as I said before, compare the newtons, joules. Oh, for goodness sake, we can't compare them yet because we haven't done it yet. As we will see. Was that what you were pointing out? I was getting used to writing newtons and then mixed up a very important point. These are energies, sort of. Okay, potential energy. To be precise, I should say change in potential energy, right? Potential energy when? Well, it changes. By how much does it change? I would think it's reasonable to define, at least for now, define this initial point as zero. Zero is our initial position. We don't have to do it that way. As it happens, it'll always cancel out if you start at a different level. The change in potential energy is the only observable. So the mg times final y is what? 2,000 times 10, 20,000 times 8, 160,000. Did I do that right? Mental math. Okay, and now is when I can make the appropriate point. Kinetic energy, 2,000. Potential energy changes, 160,000. I mean, come on. The kinetic energy of an elevator shouldn't actually be a big part of its energy. You want to go up. Doesn't matter that you're going up super fast. The purpose of an elevator is to get things from one level to another, not to make the ride exciting. Goal for an elevator designer is probably to make the elevator ride as unexciting as possible. Okay, now what's the work done by the tension force? Well, what I could do is, if I've got the magnitude of tension and I've got the magnitude of the displacement, what is that? I should be precise here as well and say the work done by tension, the external force that we've not already considered. Tension times displacement is, well, that's an interesting coincidence. The work done by tension goes entirely into gravitational potential energy. I seem to recall that I once wrote an equation that says that the change in total energy equals the total work done, right? Your central equation for this entire module, what I claimed before, every single problem that you do, if I'm not asking for just some sub-part of the problem, here is what can be used to solve any complicated scenario that I might throw at you. Total change in energy, I should be precise, change in total energy equals the work of the forces that have not been accounted for, yeah? Okay, so can we talk about the initial total? What is the initial total? It's very small. I could totally, without batting an eye, ignore things if you rounded 2,000 to 0 compared to 160,000, yeah? Okay, but if I wanted to talk about all of the forms completely in here, I could say 2250 joules. And then the final form of energy equals, I have picked up 160,000 joules of potential energy, but have I changed my velocity? No, I've still got that, kinetic energy if I haven't changed my motion. Okay, now what's the change in total energy? How do I get a change in a quantity? What does change even mean, other than that which I never carry around? Forgive me for not adding that. That's an addition even I could do in my head, but I wanted to emphasize here. Here's our initial, here's our and I wrote it backwards. I am not on my game today, my goodness. Yes, I did. Yes, I did. Yes, I did. I'm second guessing myself. Cancel, cancel. So the change in total energy, 160,000 joules. I have considered my kinetic energy and change in potential energy, right? And I claim that that is equal to the work done by forces that weren't otherwise counted. Talk to me about this. Is this surprising? Is this kind of duh? Turn to your neighbor and discuss. Then Google form whatever is next is ask me a question or reflect on this briefly. And if you have nothing to say, please don't say, I get it. Just leave H blank. So H, if you have a comment, question, ask. Ah, here's a good one. Ooh, a bunch of good ones. Okay, is that enough time to type? Question uno, does external, I should say exactly what was typed. Does W external stand for external force done? What does W stand for that begins with the letter W? Work, external work done. Yes, external work done, that is to say forces outside the system that are not already accounted for by talking about spring energy or gravitational potential energy. We calculate their total work and say that is the external work done on the object. Total external work done by forces not otherwise accounted for is the full name, but that is very long to write. I see, and I prefer to write WX. If you have a follow-up question to that, anyone have a follow-up question for that? Please. Well, tension isn't a spring or a gravitational force, so it's not already included in the energy perspective, and yet it is a force acting on the object. Right? There are two things acting on it, tension and weight. We've already accounted for weight, so that leaves tension. The tension is the only thing that can do work. Yeah. Okay. Next, really good question. I like these. Why do we not have normal force if there is a boy touching the elevator? Specifically because I said, consider this as the object under study, the elevator and everything in it. The total mass of the elevator is 2,000 kilograms. You could consider the elevator as a separate object from the stuff inside it. Then there would be a work done by the normal force, but the elevator would also be changing the gravitational potential energy of the boy. No, that's no longer part of our system. The elevator would also be doing a work on the boy. If you calculate the total change in energy, the energy stored by the elevator will be different, but it has to add up to the same. The work done by the external tension force and the boy would be the change in energy of whatever we call the system. So again, to summarize, to answer the question, why do you not consider the normal force of the boy? Because I define the boy as part of the elevator. It would change the problem. It would change the analysis, but you'll get the same results. Next, oh, I just love these, asking good questions. Does UG equals mgd, gravitational potential equals mass times gravitational field times, I've been saying delta y, but you can use whatever letter you like. Does that ever change for other problems, or can you count on that to be the same? Well, gravitational potential energy equation, mg times vertical height, whatever letter you use to symbolize that, that is a true statement. That is, I would say, the defining equation for gravitational potential energy. Do we always use it? No, if height doesn't change, if I were talking about a sled being dragged across a horizontal ground, who cares about vertical gravitational force? Doesn't do any work, doesn't store any energy. There's no change in y. So there's no need to consider gravitational potential energy. I'm not sure what the question is specifically asking. Does it change for other problems, or can we count on it to be the same? You can count on gravitational potential energy's equation to be mass of whatever is the system times gravitational field times the height of the object relative to some defined initial. Whether you always apply that depends on whether it makes sense in the context of the problem to apply it. Next question, how do I know what does work? I love these. Whatever forces act on the object, any force that acts on the object that you haven't already counted, if you are using gravitational potential energy, spring potential energy, well, those are already accounted for. Don't also calculate their work done. Every other force may do work. Remember, work can be zero if the forces are at right angles. As I run across the classroom, gravity does no work on me because it's perpendicular to my motion. I would still say I could add the work done by gravity if I wish, the work done by normal force, also zero, to my total work equation. It's just those terms are zero. You can always say that work is every force's work added together. Total work, every force that you haven't already accounted for. Question, why doesn't final energy equals initial energy plus work apply? Let's take a look at this equation that I just wrote on the board. Change in energy equals work. Well, what is change in energy? It's final. What is change in anything? It's final minus initial. Okay, let's contrast this with the equation E final equals work plus E initial. Are these different statements? These are exactly identical mathematical statements. All I've done to this is an algebraic rearrangement. I've added EI to both sides. This and this are the same equation. I end with what I started with plus what is given to me is the exact same thing as however much I change, is that what is given to me? So why doesn't that apply? It absolutely applies, and I also used it. Next question, kinetic and potential energy are in the same direction. Wait, hold on a second. Kinetic and potential energy are not directed quantities. They are not vectors. They do not have a direction. They do have the same sign. Change in potential energy is positive. We are going upward. I am increasing the stored energy, the ability to fall. Gravitational force could speed me up as I fall. That's an increase in gravitational potential energy. And kinetic energy is positive. Yes, well, kinetic energy is always positive. I do want to distinguish they have the same sign from they have different directions. There is no directionality. You can increase or decrease, but it's not an up and down. It's not a left and right, east and west, in and out of energy. Is this why we added those two values for final energy? No, you add those two values for final energy because you always add every kind of energy together to get a total energy. If you have a negative number, if I add a quantity which is negative, that can be simplified to saying I am subtracting a number. Let me be specific here. The question is, do you add things together because they have the same sign? Let's talk about a quantity if I have 2 and I have -1. I claim the total of these numbers, 2 plus -1 is indeed 1. I claim that this is 2 plus -1. I can also rewrite this as 2 minus 1. Yes, these are the same result. I think of this, though, as the total amount of work done plus change in energy. I think of this as the total. I think of this as the total of quantities, some of which may be positive, some of which may be negative. I think of the second as, well, I don't know. Well, then you have to worry about, do I add, do I subtract? It's a harder idea in my mind. I suggest you think about it like this. Always add together all the forms of energy, kinetic, gravitational, spring potential. And then if some of them are negative, yeah, well, you could simplify as needed. Why do we add all forces? Net force equals mass times acceleration. Net force is always add the forces together. If that was actually asking why do we add the energies, because, well, same answer. Net energy, E, is always the sum of the individual kinds. If I've got a checking account and a savings account, my net worth involves adding those two things together. You want to know your net worth? Well, don't ignore part of your money. Do we subtract 2,250 because there is no change in kinetic energy? No, I subtracted the initial energy off of the final energy, which had the same quantity in it. If I have 160,000 plus 2,250, and I subtract off the initial, which is 2,250, I can cancel that. I'm not subtracting 2,250 because kinetic energy doesn't change. I'm subtracting 2,250 because that's my initial, initial energy. Initial does not equal final, by the way. There is a change in energy. How much change in energy? This much change in energy, rather a large amount. Initial does not equal final. How do I know when to use the negative sign in tension? Well, I use a negative sign in any force when it applies. If I am talking about a force vector, I include a negative sign if that force is downward or leftward. I include a positive sign if it is rightward or upward or northward or whatever. If I have already accounted for the direction by drawing arrows in opposite directions, you may see me write, mg without a minus sign if I'm subtracting it off something. Well, I claim actually that's exactly the same point I was just making. I'm adding a negative quantity. Sometimes I just don't write parentheses. They're mathematically identical. Can I explain how to know if work is positive or negative? Yes, it's the same test we've been doing again and again. Force is in some direction. Displacement is in some direction. In this case, the tension force is upward. The displacement is upward. It is moving upward and being pulled upward. The angle between those is 0 degrees. Cosine of 0 is, or you can think of this as these two forces. This force is helping this displacement. This vector is pushing this vector in the direction it wants to go. This work is giving the system some energy, so it's a positive work. Work is negative when a force opposes, when the directions are opposite. When the force that is being applied is trying to suck energy out of the system, that work is negative. For more on this, review what I've said for the last 4 classes. This is what we've been doing again and again. Work is positive if the force and the displacement are in the same direction. Work is negative if they're in the opposite direction. This is a universal. This isn't just my convention either. YouTube may have a useful video on this. I promise this is not This is a universal truth. Can I go over the universal equation that I make all other equations from again? Here it is. I add up all the forms of energy at the beginning and end. I subtract off initial because that's what change in energy means. I calculate the work done by external forces not already accounted for, and the total work done by all those forces is equal to the final minus initial energy. If it makes more sense to you, if you would prefer to algebraically rearrange this, I can expand delta E into final E minus initial E and add it over to the other side of the equation. If it makes sense for you to think of, you end with what you started with plus how much you changed by, what gave you or subtracted some energy off of you, that is mathematically identical. I would say that is the equation written in two different forms, two different strings of text. Why was K the initial? Because I started low. And I think it makes a lot of sense to define that as the 0 point of height. Can I please break down each letter in Wext? Yes, absolutely. Work is always the following. Again, please look at the previous slides and everything that we have been doing. The cosine theta may be intimidating. Let me write it as this. Force times distance, no vector hats, and the negative one if oppose each other. If helping each other, and if perpendicular. I hope you can deduce that if I write perpendicular, I'm short for perpendicular there. Work is always this. Force times displacement times, if there's a plus, minus, or zero, multiplying that, there you go. Work external is any force applied to the system in question. No, it's any work being done by an external force I haven't accounted for. Force and energy are different kinds of things. You can't say external work is a force because those are very different quantities. How tall is your bank account, my friend? How much does your age weigh? It doesn't make sense to compare those two kinds of things. How much did that check deposit in your bank account is a reasonable way to say, to connect two things. Both of those might be measured in dollars, for instance. But, being specific about terminology, you can say that work external can be done by any external force on the system, applied to the system in question, remembering that spring forces and gravitational forces are already accounted for. Why is the 2250 joules initial, and why are we adding 160,000 joules to 2250 for the final? Because there are two forms of energy at the beginning. We start out with, where did I write that? We started out with kinetic energy. We ended with some gravitational potential energy and the same amount of kinetic energy. I could write this as kinetic final, but does it make a difference? This is total energy. I add together what I have. So you add them together to get the total energy because those are the kinds of energy that you possess. Would I post the old slides so I can take notes? Yes, I've posted the old slides. They've been up for a while. It's called 07.pdf. It's the only thing I posted last week, I believe. Follow-up questions to any of these? There were questions in the chat. Thank you. Okay, I was round and correct. I already answered that. Why do we account for displacement if we didn't list it in the applied forces and energies? displacement is not a force or an energy. Displacement refers to how far do you move in which direction. Now, talking about questions A and B, what forces apply and what energies apply? Well, force is a push or a pull. Energy is an accumulated ability to do things. And that is not the same kind of thing as how far have you gone and in which direction. So again, why do we account for displacement if we didn't list it in the above? Because if you're calculating work equation involves a displacement, but simply to identify what kinds of forces, what kinds of energies, you don't need to know anything about displacement. Kimmy asked, is there always going to be potential energy if the elevator was moving at all times? Well, if the elevator is moving sideways, oh, well, anytime you are going up or down, I would suggest that you account for gravitational potential energy. Yes. Why in energy final you added gravitational energy to kinetic energy, not gravitational energy alone? Because we end at the end of the problem, as I said, we are moving up as we are just about to slow down for at the fourth floor. We are both moving and we are high. If you're going somewhere, if you have motion, you have kinetic energy. If you have height change, to be precise, you have gravitational potential energy. To find a total energy, total just means put things together, add them together, add all of the things that you have together. Total energy is the sum of the individual energies. So we added gravitational to potential energy, added gravitational potential energy to kinetic energy because both of those forms were possessed at the final time. Follow up to any questions above. Okay, let's change this. Let's talk about the elevator falls and the brakes cut and the elevator bonks onto the springs. I'm going to ask you, ultimately, I want to know how far does the spring compress, but I will give you the bigly hint. You don't need that. You don't need to consider that at all. You don't need to consider the you don't need to consider the velocity before it hits at all. I can ask that separately. Okay, so again, the challenge is we're going to change the scenario. Instead of moving upward from the second floor to the fourth floor steadily, I'm going to say, oh no, the brake's cut. My upward motion goes up a little bit and then I fall and I smack into that spring. What is the maximum compression of the spring? When all of that energy that I had is stored in the spring, how pancaked is it? I do need to give you the spring constant K, and let me make something up in my head that's going to give something of a slightly maybe kind of reasonable value. I think using inside my head a quick calculation, let's say it's a very stiff spring indeed. And I think this will give a reasonable value. Let's say spring constant is 500,000. So let spring constant K, not to be confused with kinetic energy. Units for spring constant, you remember? Newtons per meter. Yeah, what is this? We're on I. Anyone need another description about the visualizing the problem? Any clarifying questions? Please. Yep. So we have gone from the second floor to the fourth floor. We are still moving upward. Oh, the string is the cable is cut. How far do we pancake that spring? I'm going to give you a couple minutes by the thing and walk around. I have so few people. I will also answer questions about any of the previous. Clarifying question about this one? We're gonna hit the ground. So what is that? Another four meters? So if second floor to fourth floor is 8, I'm gonna say each floor is 4 meters. Yeah. That is another assumption, I'll say. From the fourth floor, 1, 2, 3. So that would be what? 12 meters? Thank you. Good clarifying question. Okay, I'm gonna give you guys 5 minutes by the clock. Please. Mitzi. Okay. So gravitational potential energy and kinetic energy, we identified those previously as what happens when you go up from second floor to fourth floor. So it should make some kind of sense that we're starting this problem where the previous part left off. I have the same forms. Now here's the tricky question. We definitely end with a spring compressed, UE, elastic potential energy. What about excuse me, what about gravitational potential energy? Do we have gravitational potential energy? We're down. We're as low as we get, right? When do you not have gravitational potential energy? Sit down. When do you not have gravitational potential energy? When you're at your reference height. When you're at wherever you defined y equals 0. Gravitational potential energy, mgy. If y equals 0, then mg times y equals 0. Am I at where I set y equals 0? No, where is y equals 0? Where did I start the previous part by defining y equals 0? At floor what? At floor 2. So if I'm going to use the previous energy, to say that the total energy is just the total energy that I had previously calculated, I think I'd better be internally consistent. I think I'd better say that that energy is relative to the second floor. Now, if I go down from the fourth floor to the first floor and compress the spring, how far am I below the origin, below the position origin? I have defined this as my y equals 0. I go down, how far? I've gone down 12 meters total. And I started let's see, I moved up by 8 meters, then I went down by 4. My initial from floor 2 to floor 4 was 8. From floor 4 down to the spring is negative. Did I write that down? Did I write that down? Is 12 meters down. How far is it from floor 2 to floor 1? 4. 4 downward, negative 4. Okay, so I would say yes, there is absolutely a gravitational potential energy. These are different, but if you're not ending at wherever you set as your reference, you need to include a gravitational potential energy form. I don't know the final compression of the spring. I'm just going to call it X. Could call it lots of things, delta X. But I am going to say, what is M? What did I say M is, 2000? Times G, round, times H. I'm 4 meters below reference height, yeah? Who's confused with the -4 for final y? For reals. If I go up by 8 meters and then I drop down to the first floor, 12 meters, I am 4 meters below my start, my initial start. Okay, gravitational potential energy at the beginning and kinetic energy at the beginning. What did I have? Well, I already solved that sucker. I don't need to do this twice. I already found that my energy at the top was, well, I'd say I can add 160 to 2, 162,250. Okay. What forces acted on the falling elevator? Wait, I've been talking too much. Google question J. What forces do I need to account for in work? Google question J. What forces will I need to calculate the work done by? I will remind you that the elevator cable has been cut and that we have included gravitational and elastic potential energy terms. Hint, hint, hint. I'm going to call that time as we only have a few minutes left. Remember, I've been saying, if you are already including gravitational or spring potential energy, don't double count. Don't also calculate work done by those forces. There's only one force that acts until it hits the spring, and that's gravity. Oh, we've already accounted for that. Then gravity and spring as it moves down. Well, those are two forces that we're already accounting for in the potential energy forms. So the correct answer here, I would say, is there are no external works that I need to consider. Okay. So my final statement would be, let's see, half of 500 is 250,000 times x squared. 2,000 times 10, 20,000, minus 4 is minus 80,000, equals 162, 250. I'm going to leave this as our final thing. If you can do this correctly and solve for x, then you'll be free. Ready, set, go. Solve for x. Uh, 1 minute. Good. And my mental math was correct. Hey, turn to your neighbor and check their arithmetic, algebra. Also, you should sanity check your answer, by the way. Check whether it makes sense. This is a meter. Does it make sense that it would be 200 meters compression? I will tell you that I did give you values that are sort of, kind of, maybe reasonable-ish. Cerny, would you be willing to walk through the algebra? And now, in the last moment of class, no, Yami, this is on K. Last moment of class, let me give advice for how to solve one variable equations. We're at 1 minute, unfortunately.
I know. All right. How many people feel like they knew how to solve this? Any feedback? Ross, put your hand up. Okay. How many people felt like they did not know it? They're like absolutely stuck. You got to be honest. Give the teacher feedback. Okay. I'm going to say, this is what you're solving for, right? You guys all remember PEMDAS, right? Okay, I'm going to go real fast. So what's happening to x? He has an exponent, right? He's being multiplied, right? He's having something subtracted. So you just go backwards. Solving is the opposite. You go backwards. So I know I'm going to have to undo this piece first because that's the last in order of operations. Does that make sense? I know I'm supposed to be going fast. So I'd add 80,000 to both sides. I'd end up with 250,000 x squared to 242. Okay, then going backwards, what's the next thing I should undo to get x alone? Yep, because that's the next one on the way up, right? I'm multiplying, undo it with division. I divide both sides by that. Thank you. X squared is 0.95. And then how do you undo an exponent? A square root. X equals 0.98. Anytime you're solving, as long as you only have the variable in one place, you can use backwards order of operations. I know time is up, so I just wanted to comment that there are a few people that talk to each other in your groups and that did really well. The rest of you, I know it can be hard to talk, but you have to give the teacher feedback. And if he can hear you having your discussions, then he knows what to do next. So please think about that. This classroom should be louder. Have a wonderful day. Thank you.
Oh, yes. Sorry. My picture? Oh, the sketch.
Have a good Thanksgiving.
Of course, you too.
I just said, yeah.
Do you remember to change the?
Yes, yes. I had one question. So I did some advancement. Wait, then I had to self out by talking. But, maybe some more technical. Essentially, you're spreading press, right? We're certain. So when you have a change. So in theory, that would be
12 meters versus what, 1 meter? Oh, I can't do it.
Yeah, no.
I mean, I didn't have that when I was 10.
Yeah. No, I don't didn't have. I didn't say so. I wasn't there last week, so on the weekend. So, I went into the first one. And I didn't see last week, and that was on the weekend. I didn't see any. So when I came here on Monday, I was very surprised that talking about more than nothing makes me see anything. I'm gonna check tonight, but yeah, I don't.
If you don't see it for some reason, well, it's a big problem. Let me know. Okay?
Yeah. But that was on the weekend. I didn't see it. I don't. But I mean, you gave the extension.
Yeah. It's 15 problems. And we go home.
I know.
5:45. We'll leave with the 40. Oh, half a second. Let me hit stop recording. We've had some dead time here. Nalo, you